Very well. I think we can go ahead. So I would like to welcome everybody to today's webinar on simultaneous wireless information and power transfer, or SWIPT for short, along with my colleague Ahmed Kabir. My name is Ammar Kouki, who will guide you through today's webinar. And then I want to start off by sharing today's agenda. So we'll give you a brief introduction in the context on which we want to today's webinar is situated. So again, it's on SWIPT, and we'll cover very briefly some of the challenges that the design of SWIPT systems can pose, and we will focus more specifically on biomedical implantable devices. So that will be the focus of today's webinar. And specifically, the SWIPT system will have a hybrid coil, so for power transfer, and antennas for information transfer. So we'll go over those. I will give you a brief flavor of what kind of results to expect, but the crux of today's webinar will be really to show you through a live demo how you can do this kind of work, this kind of design and simulation. And obviously we'll have time for Q&A. And by the way, for all your questions, you can type them in the chat box as we go along, so we'll get to them at the end of today's presentation. So, okay. So do not hesitate to type in your questions as we go. So, really, SWIPT is really a wide-ranging technology, and it can mean different things to different people. Anytime you want to do simultaneously powering and transferring of power and information, you are in a SWIPT context. And this is driven in a large part by the proliferation of sensors of all kinds. Okay, and typically when you have a lot of sensors that are spatially distributed and so on, you want to communicate with these sensors. And ideally, you don't want these sensors to require batteries or some other to be plugged to an electrical network. So we want to be able to power them at the same time, communicate with them. Obviously, this can have a very good, impact in terms of reducing power consumption. And for communication systems, it's a better use of the spectrum, and even mitigate some interference issues and so on and so forth. And so the idea of being able to do this simultaneous power and information transfers is very interesting, as I said, for a wide number of reasons. But in one case in particular, which is the biomedical devices, this already takes on another importance. Anything we put in the body, implantable devices are required to be ideally, the smaller the better, the less power requirement better. If we can take out batteries, it makes smaller, it's better. So smaller is always better because of all kinds of health considerations and safety considerations and so on. So wirelessly powering these devices becomes interesting. So instead of putting something you have to take out and replace a battery and so on, you can just power it wirelessly. And obviously, these sensors need to communicate back information, these implants, so we need to be able to communicate with them. So what are the most efficient ways to communicate with these things while powering them? So this is where the SWIPT technology can become really, really interesting. However, when you talk about SWIPT in general, then there are questions that you need to be able to consider for your applications. Depending what you're doing. Again, in the biomedical context, the power transfer itself, typically in biomedical context, you're really in close proximity. So you can go with, a capacitive or inductive coupling to transfer power. And you can also consider radiative power transfer. But so for today's webinar, we'll focus on the inductive power transfer. So, and then once you do that, then what is the size, and what is the size that's required in terms of the distance, and how does it vary? How is it impacted by the distance between the external and the device and the implanted device and so on. So the power transfer efficiency becomes an issue, important. And now when it comes to communicating, is also another consideration: what frequency you want to use, how much bandwidth they require, and so on. And all along, you always have to keep in mind that you're dealing with a human body, so the tissues and safety to exposition to power and so on need to be considered. Now, the good thing is all of these things you can address in our solutions that we'll show you today, which is basically you can go from the design up all the way to the safety considerations and how much energy and how much temperature can be induced by this SWIPT system. So for today's example that we'll use, again, please consider this as a typical example. Use your imagination for whatever other scenarios you can come up with, and how you would be able to analyze them and simulate them and design them in our solution. So for today, we'll consider a typical implant. So this is a model taken straight out of our Solidworks HF solution, and you can see in this model that we consider a human body with all its properties, and we're going to focus specifically on this implantable system. So the implantable, the SWIPT system is consistent of two components. So we have the external coil that's going to power the implant, and an internal coil to receive that power. And we have two antennas on either side for communication. So this is an example, not necessarily the system or the way to do things, but just we picked this as an illustration how we can do this kind of simulations and calculations. And so in here we have concerns about this. So the external and the internal devices. And so for the power transfer, we're going to use a 13.56, an ISM band for power transfer, which is 1356 megahertz. So this is going to be an inductively coupled system. And for information transfer, we're going to consider a G-shaped antenna. And again, we'll consider two alternative ISM band frequency. What's the difference between 415 and 905 megahertz? Which one should you pick? And for the design purposes, in this case, we fix the separation H at 15 millimeters. And we obviously modeled the skin, the flat, and the fat and the muscle in this design. Okay. So this is the example that we considered, and in the live demo, we're going to show you more about this model, how it's done inside SolidWorks. And so, and the key things, the key parameters that we're looking for, obviously, is number one is how efficient are our coils in power transfer. Again, it's the better, the more efficiency, the less power requirement, the safer the whole system is going to be. So you don't want to have so much power in the presence of biological tissues. Okay. So they have two efficiencies. One is how efficiently we're powering the implant. So that's essentially an efficiency in terms of the power that's injected in the exciting coil versus the power that's received in the exciting coil, and we'll show you how to simulate this. And then for the antennas, it's actually we have two antennas, and we are transmitting from one. One is acting as a transmit and one as the receive, and that link is bidirectional and is entirely reciprocal or symmetrical. So really the transmission coefficient between the two through the tissue with its biological properties and electromagnetic properties, that would be our transmission efficiency. Now from that you can extrapolate for a communication link and so on, how much power is required, what's your signal to noise ratio, and so on and so forth. But the key parameter there is this how is the power radiated and how is it coupled from one antenna to the other, and you can use that into a kind of a link budget analysis. So with that, we've done this, and we'll show you this now in two steps. So first, we actually focused on getting a resonant coupling for the power transfer, and my colleague Ahmed is going to show you briefly in EMS how we do this, so you can build the whole circuit and so on. And we're after this efficiency calculation versus so input power versus frequency. Okay, So we can see that we can actually get a pretty good efficiency, and we can center our design around 13.56 megahertz. Again, when you do that in the model, you're able to see a whole bunch of results. Ahmed will give more details about this, the flux densities and so on, the currents, and you can even go and see how much specific absorption ratio is happening, okay, in this. So we can see that how safe the system is from the arrangement and the exciting currents levels that you're using and so on and so forth. Now, once that is done, the next phase is essentially to add the antennas and simulate. And here again, the key things we're looking for is, to center our antennas to operate at the SM band and get maximum efficiency. So we'll show you in the second part of this live demo how this is obtained when we do the antenna simulations for this. And we can see that we can have some tune our system for 415 megahertz and get some relatively low efficiency at 415. If we go to 905, well, we can still tune our antenna system, size it and dimension it properly, but we can get significantly better efficiency at this frequency. So you can see that a good combination would probably be use 1356 for powering and 905 for communication, and you build your device based on these specs. And again, when we do the electromagnetic, the antenna simulation, we can also look at the electric field and specific absorption ratio at different frequencies and so on. So this is a flavor of what we expect in today's demo, in today's webinar. So at this point, I would like to hand it over to my colleague Ahmed to show us how we can do the wireless power transfer section through inductive coupling. And then I'll come back and show you how we did the antenna simulation after that. So Ahmed, if you will.
Well, thank you, Amar, for the introduction and welcome to this part of the presentation. You can all see my screen.
Yes.
Yes, Amar?
Yes, we see it.
All right. So, as introduced by Amar, the inductive part of this is done through our what we call low frequency electromagnetic simulator, EMS, okay, which is integrated in Solidworks. So because we are doing low frequency, well, 13.6 megahertz is not low frequency if you look at the itself, but if you look at the whole EM spectrum, it's a very low frequency. Yeah. If you compare it to light or to millimeter waves or other frequency bands. So the good thing about that is you really care only about if you model only if you have ferromagnetic material or if you have high conductivity. In this particular case, we just simply, because of the tissues, fat and bones and all of that, they're not magnetic. So it's really consider it like just air. So show you just the two coils, how they can communicate each other, how we can compute the efficiency and the coupling coefficients. So EMS, it's very easy to create a study. So you click the study, okay, and for this type of application, you're going to use either AC magnetic, okay, or time harmonic, or transient magnetic. In this case, it's AC magnetic, so you're going to specify a frequency of 13.6 megahertz, okay? And you can parameterize distances or even frequency, okay? And you can computing circuit parameters. This is the most important thing. You make sure that you click on this, and if you wish, you can also couple to thermal, structural, circuit, so on and so forth. So we have many actually videos in our YouTube channel where it gives you in detail how to create a study, how to create material. So I'm just, because we don't have a lot of time today, I'm just gonna dive straight into the results and show you. So this is the first example, is a simple wireless power transfer, okay? And then I'm going to show you the resonance wire power transfer, and then explain what's the difference between them. Okay? So, so this one is a parametric study where parameterize the distance between the transmitting and receiving coils. Materials, again, as I said earlier, the only material you have is really copper. The rest is air. So if you want to show the air with it, this is just the air around it. Okay. Wait. Where's my air? Okay. So this is the air region around it. So, okay. So I'm going to go ahead and hide the air again. The rest is straightforward, really, because the fat, all the biological tissues are non-magnetic. So really, we don't need to model them. You could if you wish, but I just want to simplify the model for you and just to show you how easy it is to really use EMS to model your wireless power transfer. So we have a design scenario, okay, where we parameterize the distance between transmitting and receiving coils. Okay, so it's 2, 7, 12, 17, all the way to 40 millimeter distance between the coils. All right, so first set of results, which is the most important, is what we call the results table. These are what we call lumped electrical and mechanical properties, which we don't care too much about the mechanical part in this particular study. So for each scenario, we have inductance, current, flux linkage, impedance, resistance, coupling coefficients, all of these, okay, for your study. And in this particular case, what we care most about is really the mutual inductance as well as the coupling coefficient. Okay, so this tells you how much coupling takes place between the coils, or the receiving and transmitting coil, and you can plot this as a function of scenario. Okay, so in this case, as you can see, with the further we get from the transmitter, the receiving coils, unfortunately, the coupling becomes smaller and smaller, as you can expect, and this is one of the problem with the basic wireless power transfer is very dependent on the distance between the coils. Okay, you can view the results in a text format if you wish. Okay, that's one set of results. You can also look at the inductance if you look at the mutual inductance, and also it is also very dependent on the distance between the coils. Okay, any of these quantities, the resistance, impedance, flux linkage, all of them are plottable as a function of scenarios here, where we have 9 scenarios here. Of course, you can export this data to for all scenarios. You can print it. You can so that's one set of the results that you get with the EMS study. Of course, you can look at the plot, the H and B, the magnetic flux density B, and the magnetic field H, applied current. If you look at the current in the coils, okay, you can, if you want to include the air, I can include the air, okay, and if I want to do this is my magnetic flux. Wait, this one is okay. Yeah, I think, let me show it in the other case where I have parameterized actually this case. I have parameterized the alignment. Okay, I think the other study needs to be rerun. Okay, and this one I can do clipping. section clipping, okay, and I can let me see. What's happening to the clipping? Okay, so I can plot on. There's so much data, that's why it's taking a little bit of time. All right, there you go. You can plot in section only. Okay. And then, as you can see, I can see my magnetic flux density, where I can also animate it as a function of the cut. If I want to see a different cuts, this particular study, I parameterize the alignment between the coil, and also if I go to the coupling coefficient, they also, the alignment also is important, you know, as the more misalignment between the axes of the coils, the lower is the coupling coefficient, and so also the efficiency, because the efficiency really directly depends on the coupling coefficients and the mutual inductance. So you can plot any of this data. This one is the applied current in the coils. Well, because I have the air, so I can edit definition. If I want to see the plot only in coils, I can plot, say, this coil, and this is the receiving coil, 0. But let me see. There you go. So this is my current, because there is no current in the receiving coil. All the current is, of course, obviously applied in the transmitting coil. So any of these data you can look, you have a lot of results, whether field data or tabular results. Okay, that's one set of the results. Let me go to the next type of study, is what we call a resonance power transfer. And the resonance power transfer, was discovered or suggested by MIT research in 2008, and now it's becoming the standard. Let me hide this. In an effort to overcome the dependence, the big dependence on the distance and the low efficiency seen by standard wireless power transfer, the researchers have a genius idea, actually, very interesting idea, by saying, okay, how about if we add a capacitance, okay, and then all of a sudden you're going to start having resonance, because you're going to have the inductance of the coil. Of course, the resistance was there. By adding a capacitance, you can actually achieve a resonance in this circuit. Okay, and then they showed and proved that, well, if you choose a frequency equal to the resonant frequency of your individual circuit, okay, it has to be the same resonant frequency for both. You have to tune it until you achieve resonant frequency. You actually achieve much better efficiency, as the slide shown by Amar earlier. Okay, so in EMS, that is done. It's very simple. When you define your study, you say coupling, and you say, I would like to couple the circuits, and then you're going to have your circuit case. Of course, you can have different, like in these cases, I have different resonance circuits. It's the only difference between them is the load. Okay, one is 10 ohm, and the other one is 50 ohm. You can study that as well. So by tuning your circuit, okay, you actually can achieve a much better coupling. So if you look at the, where's my coupling coefficient? Okay, you see, I didn't do a parametric study here, but the coupling is really much higher. Okay, and the efficiency at the resonant frequency, you achieve much better resonance. So what's the difference between these two studies? The resonance wired power transfer, the regular wired power transfer, is really the addition of this capacitance. Okay, other than that, it's just a regular study. Okay, by coupling to this, you can, of course, you can all the rest of this. The plot is the magnetic flux density, the all the field data remains, you know, you can also plot it. Of course, it's different. You can have much better coupling between them. Let me see here what I'm showing. Let me see, 1 second. I can again do a clipping at this level. Okay. It's taking a minute because I'm just using a laptop here, and the so to conclude, using EMS, you can easily study whether you have your all the properties, the okay, the field, and so this is your field. You can also animate it, and so you can look at both the field data uh, and the circuit data. Okay, and the, of course, if you wish, you could do coupling to thermal and so on and so forth. But in this particular case, we just wanted to show you the power of EMS, how you can use it to study both the wireless power transfer and the resonance power transfer. And I'm repeating again, if you have at this frequency, you only care about if you have magnetic material. So the specific tissue really does not affect your resonance, the power transfer at all, and this is a good part of the an advantage for EMS. So I think this for this I would like to thank you again, and pass again to Amar to present the high frequency part. Thank you.
Okay. So thank you, Ahmed. So don't forget, if you have questions, please type them into the chat box. Okay. So so let me just go back again and share my screen. So I just wanted to, you know, maybe add to what some of what Ahmed said and so on. So I don't know how many of you are SolidWorks users or not. And one of the things that's important for us to embed in SolidWorks is this kind of thing. So if you actually want to do, you want to simulate the whole thing, and you want to have a realistic model of a human body, it's you know, you really need a powerful CAD to do that. So that's one of the reasons that we do this. So in this case, so I'm going back to the SolidWorks starting point, and we consider this phantom, this model, and we're focusing on this implant. That's probably a heart implant or something, maybe a pacemaker or something like that, and we're doing this around the heart. And the nice thing about SolidWorks is you can actually build what we call multi-configurations. So essentially, if you have this, you really don't need to model the whole thing and simulate the whole thing and so on. You can focus on one section. So you can create what we call multiple configurations. Okay. So now I have the whole assembly. This one I'm not simulating because I don't want to mesh and model all this. I want to focus on this one. So in this one, when it comes to designing the antennas, it turns out, obviously, for antennas, antennas are intrinsically related to the frequency that you work on. So if you are at higher frequencies, usually your antenna gets smaller, at lower frequency, and then gets larger. So we don't have the same antenna for 415 and 905 megahertz. So that's why we have two configurations. It's all one environment. It's all one work environment. Okay. So if I go to activate the 415 megahertz configuration, then we see, okay, I actually focused on this part. The phenomena are localized around the implant and the reader, if you will. Okay, that's going to communicate with it. So that's what we model. Okay. Now, unlike the low frequency, where the body, the material properties of the body are non-magnetic and will not impact the power transfer, at high frequency, they're important. So we have to model them. And you can see here a few layers of material that are modeled. So this is essentially my reader, if you will. And on the other side, I don't know if you can see this, I have my implant, if you will. Okay, and if I if I isolate this, okay, you can see that I have my full structure here. So I have my coils that I'm going to use for power transfer, and this is my G-shaped antenna. Obviously, the complexity of this is really up to you. Okay, it's just I'm showing you an example, but this could be something much more complex. It could even be that the same antenna, you want to use it for dual frequency, for power transfer. So this doesn't necessarily have to be two different conductors. So it's really up to you how you make this design. I just wanted to make sure that that point is clear. So you don't have to necessarily have two structures. It's really up to you. Okay. The other thing I wanted to mention before I go forward. So yes, we're talking about this medical application, but what happens for SWIPT for larger things? So you have to realize our software is based on the finite element. So you're not, if you have a network of sensors that are distributed over very large distances, you don't model and mesh the whole thing. You really need to model the small areas, and obviously between the two, you can use a standard link, propagation link equation, like Friis formula or something like that, to see how your link is going to happen. But really, that's what you want to do. So with the modeling done, and so this is our model, okay, in this case. So again, like EMS, HFWorks is our high frequency package. Okay, so this will do a full wave solution. In other words, we just do we consider all kinds of phenomena with electromagnetics, displacement current, impressed current, and everything. Okay. Whereas at low frequency, we don't consider displacement current. It's negligible at lower frequencies. The concept is, again, straightforward. You have, every time you want to simulate something, you need to do a study. At high frequency, you can have multiple different types of studies. So in this case, since we're having radiation and antennas, we're going to do antennas. Okay. We could also conceivably do S parameters if we don't expect so much radiation to leak off. So you do antennas when you expect radiation to leak away and propagate away from your antenna structure. And S parameter is really something that we use for frequency responsive systems, or maybe between interconnects and things where we really the energy is essentially confined to propagation. And you can also do some time domain simulation and the resonance analysis. So this is all done the same way. So in this case, if we were to do an antenna simulation, and I have already some studies, I just want to very briefly walk you through some key takeaways that you need. So the one thing, you can decide what your frequency sweep is going to be. You can sweep, do a fast sweep, so that it gives you an ability to do a frequency response with quick calculation. So you have all kinds of controls on how you do the frequency simulation. You have some controls on the meshing. And importantly, for these kinds of applications, especially biomedical, we might want to consider the thermal coupling. So if we do turn on the thermal coupling, and let's say we do take these defaults, and we say, okay, then you get what we call a study and the study structure. The important thing I wanted to stress in this one is that if I look at the phantom, this is part of the phantom of the human body, and it essentially has a body one, which is, in this case, I'm going to go back to my, this is the dry skin, the second one is fat, and the third one is muscle. And the important thing is before you do simulation, all materials have to be defined. So I have an air box that I'm hiding, and just apply. I need to apply material to it as well. So I can use favorite material to apply to. But when it comes to these guys, so this is my dry skin, I need to apply skin properties. And the good thing is we have a whole directory or library of materials for all these biological tissues and so on, and even for food and other things. So this you don't have to, most likely what you need for human tissues and blood and so on, you'll find it here. So if this were like fat and I can use the model at 1 gigahertz, and because I'm close to that model, I say, okay. So that's how you do to apply materials. Notice that if I double click on this, important things, conductivity, loss tangent. So this is essentially, has a big impact. It's going to have a big impact on how much energy gets transferred between the transmit antenna and the receive antenna, or between the transmit antenna and the implant. So this is important to keep in mind, and we make that easy for you. Unfortunately, we don't have time to go you through all of this. It's really straightforward. If two materials are the same, this drag and drop capability is there to make it easy for you to do, and so on and so forth. So I wanted just that part, at least I wanted to go through. The rest, I'm not going to detail how we set up the study and simulate, but I'm just going to switch back and go back to this study at 415 megahertz. So we did this. So we simulated this. To do it, we had the materials. I showed you, we defined everything. So what each body, so there's some copper, some Teflon, some FR4, substrate, whatever. These are all part of the material library. You can define your own, obviously, and so on. So everything has materials. And then we needed to define some boundary conditions. So there are boundary conditions that the software figures out automatically if you use copper, so it knows it has an imperfect conductor boundary condition. And then you can apply others explicitly. In this case, we said that we might have some leakage of energy, so we put a radiation boundary condition. And then we had, some ports, port excitations. So that's where we send the signal in and where we measure the signal out. So these are the boundary conditions. We did, this is a finite element package, so we did the meshing and so on. And the important thing is essentially to go to the results. So essentially, like Ahmed said, similar to the low frequency, we group them in different categories. So you have your field results, so anything with this kind of shaded plot kind of thing. We also compute loss density. So you want to see how much power is being dissipated in a tissue, and this could be is useful for safety considerations, obviously. How much power is lost, the total loss in the structure. And then we go their excitations, how is the field going in and out of the structure, so what we call the port fields. Then you get these circuit parameters. So how well matched is the structure? Is it operating well at this frequency? Okay, so you want to see the frequency response. You can go and do 2D plots. You can plot it as a 2D or a Smith chart plot, and you can look at parameters like S11. So for those who are not familiar, that's essentially the level of input matching. So we can see that at around 405 here, okay, I have a better than 15 dB return loss. So this structure is quite well matched. Okay. Now the other question is so that's for antenna 1. For antenna 2, okay, the second antenna, okay, and we see some glitches where this thing is resonating a little bit with this metallic structures around it. So that we capture, but it's well tuned. Okay, it's well matched at our operating frequency. So that's good. So now the question goes is, how much is this transmission coefficient? How much energy is being coupled? And that you can find, wow, that's, it's quite low. Some energy is being leaked around, okay, around the antenna, and some is being dissipated in the tissue. We saw that we have high loss tangents for these materials, so we expect that the transmission is going to be low, and so on and so forth. So this is the data. You can obviously go and look at this in tabular format and see each point with how much transmission you're getting, and then from there you are able to see how much your efficiency that you're getting from this design. You can also look at how is the antenna behave. So if we look at the antenna, we have two antennas. So if you look at the antenna, if we say that how much power is injected to the system, so we see that antenna 1 has 15 dB match, antenna 2 has 22 dB match, and we can look at these antenna parameters in tabular results, or we can look at radiation patterns, okay, of antennas and so on. So this is where you get your antenna behavior. So that's this study. The safety question, and to illustrate this, we did the same configuration for 15 megahertz, but we did thermal coupling. So we wanted to see what happens, okay, if we excite this system as a function of power. So I'm gonna maybe unlock this study. So this is currently being locked, it's not to prevent any accidental changes to my results. So this has been simulated. Now the difference between these two studies is you see that we have this additional folder called coupling cases. So let's assume you have this system and you have its electromagnetic properties. The coupling cases allow you to say, okay, for this scenario, if I injected, you can create a new coupling case, okay? You can do a steady state thermal or transient thermal. So let's say I wanted to do a steady state thermal. It's going to say, okay, I have 2 ports. I want to send in port 1. So I'm in port 1. How much power? Well, I don't want 1 watt. 1 watt probably is going to cook something. Okay. So you can say, okay, what if I send 25 milliwatt? Or what if I said 100 milliwatt or whatever? So I can say, or 10 milliwatt. Okay. So that would be 0.01. Okay. And for phased array antennas, this is important. In our case, it's not critical, so you can also control the phase. And if you create a new coupling case, so we have, you know, coupling. I can edit this name. I can call it 10 milliwatt. So you see, I hope you get this this idea. That's how it works. So what happens? How does this work? It's going to take the electromagnetic property and scale it by sending 10 milliwatts in port 1. For 10 milliwatts, we're going to get some dissipation in the model, in the various tissues. Okay, that power dissipation becomes a heat source, and that's how we solve the problem. So let me show you how we did with, again, in the interest of time, what we did with this 100 milliwatt. So we said, okay, what if we sent, you know, 20 dBm or 100 milliwatt into the system, and what's the temperature distribution look like? Okay, so now I can go and see, okay, so this is essentially telling me I have a temperature range between 37, which we use as the background temperature for the body, and we have a localized heating, you know, at the interface. It can go up to 38.55, and that's really more concentrated, very close to this exciting antenna. Obviously, we can do the same types of things as, you know, plot clipping and sectioning, or we can do overlays, and we can do a lot of post-processing of these results. Okay, so that is the kind of thing you can do with this. Now, the other thing we've done is we did this other study, and you see this is right now it's a different geometry, so it's not activated. So we tried the 905 megahertz. Okay, so I can go and, you know, collapse these studies and go to this one, and I can activate this one. So I can activate this configuration. Now this configuration, the geometry of the antenna is different, slightly different. And if we look at this antenna, so this is centered around 900 megahertz, 905. Okay, so at 905 megahertz, I am about 20 dB, 18.73 dB. So that's pretty good. Same thing for the second antenna is also matched. And then my S21, we notice the S21 is a little bit better than the other one. So I have better coupling. And this is kind of natural a bit to expect, because at higher frequencies, with this being in the near field of the one antenna, almost in the near field of the other, as you go in a higher frequency, the link becomes more directional, and you get more efficiency out of these antennas. Okay, so I hope I gave you a flavor of what you can do. The important thing is really to realize that what you are able to do with this. If you combine the power of SolidWorks, you can model very complex structures, and the flexibility of EMS and HFWorks, and you can do all kinds of simulations to predict what happens. Again, if you had the same antenna for power, like radiative power and communication, then obviously one configuration is enough. One simulation with HFWorks would be enough. If you want to use two modalities, you want to do inductive coupling and antennas, you can do that as well, and you can simulate that. Okay. So I hope this gives you a good idea. I think I would like probably to encourage the remaining time, maybe even if we want to show you some more things, we could show it in answer to questions. So if there are any questions, I would love to answer them for you. Okay, question about this circuit coupling. Yeah, the circuit coupling in EMS. We have our own circuit editor, and I think Ahmed showed you briefly the interface. So you can actually build not just that simple circuit. So you can have a combination of other networks. The circuit network is up to you. You design it, and you create it in EMS, and then you couple it to the 3D model. So the circuit and the 3D couple typically they would couple at coil interfaces. Any other questions? So there is a question about using switches, diodes, I believe the coming release of EMS, I believe, supports these nonlinear devices. So you can add switches and diodes in the circuit model to model the power systems, the power transfer system. Any other questions? Yeah, the question is, if we're selecting ports, can we do overlay multiple port results? I don't believe it's feasible in the current version. Just go back to sharing my screen. I will try it to, what is this one? So let's see if I go here and maybe do the port results. I think, because if I do a plot electric field, can I port 2 mode 1? Can I plot both? I think so. It allowed me to do this. So I think you can see, yeah, it's feasible. I've never done it before, so thank you for the question. Yeah, so it's that is feasible. Okay, you can do that, and you can see. In this case, there are two TEM modes, two coaxial, so that becomes distribution is nice and symmetric and easy. So you can see that this is my one port, and this is the other one. If you turn it, you can see it. Yeah. So yeah. You can see the two ports. Okay, let me go back to my two questions. Let me try to answer both of them. So one is it possible to solve both transient and steady state thermal within the same study? I believe so. So I think it's if I go back to where is my because just to start with that transient end. So each coupling case is different. So we can do say let me reactivate this study, this configuration. Go back to the 415 megahertz. Okay. So when I do coupling, okay, I have my 100 milliwatts is a steady state. I can go and do a new one and do a transient. So what's transient? So what if you want to look, and this is a good question. A steady state means you keep applying power for forever, okay, until things reach steady state, and that's not the realistic scenario. So typically, what you want to do is you want to come next to this implant and talk to it for a few milliseconds or a few seconds. Okay, so you can do the same kind of thing. Let's say we can go even 100 milliwatt or 0.1 watt or maybe 200 milliwatts. And then you can go and do the transient settings. And this is where you start to play with this, interval. So you can say the first, 0.1 seconds, I want to start with, that's my first time interval. Okay. And then you keep adding new intervals to that. Okay. So you can do you can step this, you can shape this transient behavior of power. You can ramp up power according to a profile that you want. Okay, so that's totally feasible. We can have steady state and transient in the same thing. The other question was about the charts. So the charts, I presume you're talking about these S parameter plots. So let me show you how that is done. So if I go here and say, okay, new plot, I want to do a 2D chart. So you can bring this is study called thermal analysis study. So I can get the S11 of that one. Okay, I can add in dB, and I can do the S21 in one chart. I can go and bring another one from let's say study 1. Okay, I can add S22 from that one if I want, or any parameter. So you can see, and then when you say okay, you get this superposition of plots. Okay, and obviously you can do the same thing with Smith chart. So if I wanted to look at S11 in the Smith chart, so I can go here and say, okay, add S11 from this study versus, let's say, because these are the active configuration right now. So these are all 415 megahertz. They're going to all look the same. So you get your S parameters in a Smith chart. Okay. And you can go and so I hope that answered that question more clearly this time. It's not scrolling up for me. Here, sorry. If you go here, you have this demo viewer. Okay. So hold just a second. It's gonna load. So you have some tutorials, step-by-step tutorials that you can follow. And you have a whole bunch of examples that are essentially ready for you. Let's say you want to work on 5G antenna or antenna near head or something like that. Okay. So if you wanted to see how this problem is set up, I can say this one and say open this. Okay. So you load this, it comes into SolidWorks. This problem is already ready for you. All you have to do, you can come here and say, okay, what is this? Oh, this is air, so no problem. So we can see what is my substrate. It has one body. If you double click on it, you can see that what is its characteristics. If you want to change the material, you say apply material. You go to the material library, you say, okay, this is actually, I want it to be plastic or something. Or I'm going to go to semiconductor substrate, it's sapphire or something. And you go and, so you can use these because they are already preset. You can say, okay, what are the boundary conditions that are used? If I click on perfect conductor, it highlights it for me. So you see, where is my conductor? Which parts are my conductor? Okay, where is my port? If I see the port. I have a hidden part, which is air. I can show it. Okay, and if I show the air, I can make it transparent, so you can see inside it. So now you can see how this full model is. Okay, how we simulate this antenna. Where is the conductor? Here is the conductor. Okay, and you can see it. Where is the port? This is the port. By the way, you can show symbol on the port. So you can say symbol. So that's my port. That's where the port is. Okay? You can hide symbol. So there are a lot of things that we put at your disposal. So for this study, if you wanted to, you just click, say run. It's set up to be solved. So you don't have to, but you can use it also to see how things are done. And that being said, again, the first starting point I would recommend is really to go into this demo viewer and go to the tutorial section. Okay, pick one of these tutorials and follow it. So these are antenna tutorials. You have S parameter tutorials, TDR tutorial, resonance tutorial, multi-physics tutorial, parameterization, how you do parameterization. So without even going to the other videos, the online videos and our YouTube channel and so on, you have a lot of material that you can use to help you get started and get trained. We obviously also provide online support and online training for users. And if you are already a SolidWorks user, you've noticed that our products are gold certified. So basically they conform, they use the same user interface, same look and feel, same workflow as SolidWorks. So the learning curve for people who already know SolidWorks is really, really short. If you don't know SolidWorks, I'm an electrical engineer, and I found this SolidWorks was quite easy for me to pick up the essentials. I'm not an expert, but I really can get around and do things that I need to do easily. It's a very powerful tool and quite intuitive and easy. Any more questions? So I think if there are no more questions, we'll probably end it here for today. I would like to thank everybody again for attending today's webinar, and you have our contact information. Please feel free to connect with us. We'll be sending you a registration link for today's webinar if you want to look at it again, and if you come across questions or need maybe to get your hands on a trial or somewhere, please feel free to reach out to us. So thank you all, and have a great rest of the day.